Now let us consider question 2 of this paper. As usual, we are going to read the question and then look at the solution. A block X slides along a horizontal frictionless surface towards a stationary block Y as illustrated in figure 2.1. There are no resistance forces acting on block X as it moves towards block Y. At time is equal to 0, block X has momentum 0.4 kilograms meter per second. A short time later, the blocks collide and then separate. The variation with time t of the momentum of the blocks is as shown in figure 2.2. This figure 2.2. So this is the way X was moving before it collides with Y. At this particular instant of time, it collides with Y and Y starts to move. Y starts to move in the same direction, that is to the right. And this is how the momentum of Y increases with the time, and momentum of Y increases with the time in this duration of time. And remember, its momentum is increasing because it is in contact with X. At this particular instant of time, they separate, and momentum of Y remains constant at 0.5 kilograms meter per second, of course, to the right. Let's look at the questions that follow. The first question is define linear momentum. Okay, we'll not read all the questions because after coming across part of the question, we'll read it and then look at the solution. Let's start by looking at the solution to part 1. Let's look at the solution to part 1, where we are asked to define linear momentum. Define linear momentum. Momentum is defined as the product of the mass of the object and its velocity. Product of the mass of the object and its velocity. In fact, that is why the units of momentum are kilograms meter per second. You could also say that linear momentum is defined by this equation. Linear momentum is equal to mass times velocity. So there are two ways in which you can give the definition of a physical quantity. You can either state it as a sentence like this, describing exactly what we have here, or you could give this equation which is associated with the definition of the physical quantity. In giving the equation, be careful to use words. Momentum equal to mass times velocity. These are words. Do not use symbols. If you were to use symbols, like for example, you know the symbol of momentum is P, this is mass M, and this is velocity V. So in symbols, P is equal to M times V. If you give it in symbols, then you must define what each symbol stands for. For example, if you write P equal to M times V, you must say where a P is momentum, M is mass, and V is velocity. But why go through that route while it's quite clear that you can give a simple expression like this to define that physical quantity? Again, here we remind ourselves that definition of a physical quantity is simply a way of showing how that physical quantity is obtained from other physical quantities. Let's look at B. In part B, we are asked to use figure 2.2. That's why I have that figure over there so that we can make reference to it to determine the time interval over which the blocks are in contact with each other. Of course, we have said that the X touches Y at this instant of time at the 60th millisecond, and they separate at the 100th millisecond. So you can see this is 100 minus 60, which is 40 milliseconds. So that is the time in which they are in contact. So they are in contact over a period of 40 milliseconds. Describe without a calculation the magnitude of the acceleration of block Y from the time t is equals to 20 to 80 to t is equal to 100 milliseconds. Again, here at 80 milliseconds, this is the momentum. At 100 milliseconds, this is the momentum. You can see that it is a straight line, and you can see that the momentum of a Y is increasing uniformly. This means that the acceleration must be uniform. The acceleration must be uniform. So the magnitude of the acceleration is constant. The magnitude of the acceleration is constant. How about over the time 100 to 120 milliseconds? 100 to 120 milliseconds, the momentum is uniform, showing that the velocity is uniform. Since the velocity is uniform, acceleration is 0. So over that interval of time, the acceleration is 0, as shown over there. So let's go to part C. Use figure 2.2 to determine the magnitude of the force exerted by block X on block Y. We must remember that force is defined as a rate of change of momentum. A change in momentum divided by time. And that is exactly why when we look at this graph here, momentum is on the y-axis, while we have time on the x-axis. This shows that the gradient, this change divided by this change, will give us a rate of change of momentum. And the rate of change of momentum is force. That's why we must work out the gradient. Okay? And when we work out the gradient, change in y divided by change in t. And remember, t has to be in seconds. That is why I divide this change in time, which is in milliseconds, by 1000 to convert it into seconds. We get we get 12.5 newtons. That is approximately 13 newtons to two significant figures, because you can see the quantities which are used in the calculation are two significant figures. This is to one significant figure, and this is to two significant figures. So we have to state that to the least number of significant figures, which is either 1 or 1 more. Let me explain that, because it's very important. It's very important for you to understand why we have written 12.5 as 13 newtons, okay? When you look at the change in y, this is one significant figure. This is one significant figure. And the time here is two significant figures, okay? Two significant figures. So the rule is the answer we get from a calculation where the values used were one significant figure and two significant figures, we write the answer using the least significant figures, which is 1. We are allowed to add 1 more. Okay, that's why we write our answer here to two significant figures. 13 is to two significant figures, because 12.5 is 3 significant figures, but 13 is 2 significant figures. So I hope you have understood that particular rule. Now let's look at part D. On figure 2.2, sketch the variation of the momentum of block X with the time t from t is equals to 0 to t is equals to 160. To t is equals to 160. And this is how it will look like. Remember, before they collide, because they collide at this particular point, remember the momentum of y was 0, but momentum of x was 0.5. 0.4. So, and it was uniform. So there is this straight line here showing its momentum before they collide. After they collide, the momentum of y starts increasing to the right. Starts increasing to the right from 0 up to 0.5 kilograms meter per second. So the momentum of x must decrease from 0.4 meters per second, kilograms meter per second, to the right all the way to 0. Okay, first of all, it has to reduce to 0 and then start increasing in the opposite direction until the change in momentum. The change in momentum of x, which is from here all the way to here, is exactly equal to the change in momentum of y. Look at the change in momentum of y. The momentum of y increased from 0 all the way to 0.5 kilograms meter per second. So the change in momentum of x must be from 0.4 all the way to minus 0.1. You can see again that one is a change of 0.5 kilograms meter per second, but it must be moving in the opposite direction. That is why it crosses over to this other side here, because it does not become stationary. Okay, it hits y at this point, then its momentum reduces all the way from 0.4 to 0, but because the change in momentum of x must be equal to the change in momentum of y, why must the two changes be the same? Why must the two changes be the same? The two changes must be the same because the change in momentum of the system, the change in momentum of the system must be 0, so that total momentum before they collide is equals to total momentum after they collide. Let's look at the total momentum after they collide. This body y has got a positive momentum of 0.5 kilograms meter per second. Body x has a momentum of minus 0.1 kilograms meter per second. If you add the two, you will get 0.4. 0.5 plus minus 0.1, you will get 0.4. That is why this one has to reduce to 0 and then increase in the opposite direction, so that its change in momentum all the way from here to this point must be equal to the change in momentum of y all the way from here to this point. I hope you have understood that particular point. So for the 3 marks, you will get a mark for drawing this horizontal line here, that one, and then drawing this straight line at this point. It must start from that point all the way to this point, another 1 mark, and the last 1 mark comes here. So make sure that you have understood how we've arrived at the answer to this particular part of the question.